Okay, so let's start the story of how planets on other stars were discovered. And it started in the most unlikely way imaginable. So let's take our minds back to 1990. Back then, no planets had been found around other stars, and basically no one thought it was possible. For all the reasons we've just gone through, it seemed to be really, really hard. People might have thought that maybe 50 years from now it would be something you'd solve, but it wasn't on anyone's near-term horizons.
I remember it was my first year of graduate school, and yeah, I said, well, someday we'll be able to do it, but certainly not in the next, during my lifetime.
But then everything changed, and it changed in a really unlikely place. So, Brian, we've got all the different sorts of stars in our galaxy. We've got yellow dwarfs like our sun, red giants, blue supergiants. Of all these stars, which one would you say is the least likely type to have planets? The one place where you can guarantee there would not be planets?
Well, I think, I study these massive stars that explode as supernovae, and so I would think that the remnant of a supernova, a neutron star, this incredibly dense thing that the center of a massive star collapses down to. So that's a star about 10 kilometers across that weighs 1.5 times the sun. That would be a place I would struggle to imagine how you might possibly get a planet there.
So these neutron stars, these spinning basically balls of neutrons 10 kilometers across, we can see them because for some reason it's not really well understood. Often they emit beams of radio waves. As the radio waves spin around like a lighthouse, every time they pass towards us we see a flash. See something going blip, 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 flashing at radio waves. That's a pulsar, which is another name for a neutron star that's pulsing. But why will you be so sure that these things would not have planets?
Well, I think there's a couple things. That first of all, the stars that create these things only last for about 5 to 10 million years. It's not even clear if that's long enough to form planets in the first place around the first stars. But when these stars die, they explode as a giant supernova. So they have 10 solar masses of stuff that are shooting out at high range, and whatever planet's there is going to be obliterated, and if it's not obliterated, it's probably going to, no longer be bound to the star and go off into interstellar space. So there's so many reasons why they shouldn't be there. I can't really count them all.
Okay, so we're all agreed that the one place where you should absolutely not find planets, the one sort of star you should not see planets around, is pulsars or other neutron stars.
Yeah.
And of course, that is the very first place where planets were seen around other stars. So let's tell you this rather unlikely story. Now, it all starts with this telescope, the Green Bank 300-foot telescope in the United States.
So that's one of the largest radio telescopes in the world back in 19...
Was.
Yeah.
But then one morning, the astronomers found it had turned into this.
That would have been a bad day.
It was indeed a bad day. And you can imagine what effect this news had on the rest of the astronomers around the world.
Yes, so, we always like to be safety conscious, and so when I would have seen that, if I was running an observatory, I would have said, I think we better check the joints and everything in our radio telescope to make sure it doesn't end up as a heap of rubble.
And this is indeed exactly what happened for this, the world's biggest radio telescope, the one at Arecibo in Puerto Rico. The amazing telescope, what they've done here is actually find a limestone valley and completely carpet it with telescope. You can only look straight up, but by moving this focus cabin around a little bit, you can look a little bit left and right.
Right, and so instead of being steerable like the Green Bank telescope is, this one literally is stuck to the ground, but it allows it to make it much, much bigger by putting this mesh of metal which goes through and essentially fills this perfectly looking, spheric paraboloid shape. And so that will then focus the radio's antennas depending on exactly where the radio waves are coming down. The antenna focuses the radio waves on a part of the sky where you can move this giant collector of radio, and essentially a little radio antenna itself that you can move around the top of the dish, and so you can point to parts of the sky with this dish that doesn't move by moving this around, because the radios will go into the different part of the sky depending on where the light wave's coming from.
So normally people competed fiercely to get time on this telescope, and they'd say, I want to look at this object, and so this dish would be slid over to the relevant place so you could see one particular object. But the managers here were paranoid. Could this collapse happen to us? So they decided to take the telescope offline for a few months while they went over and double-checked every beam, girder, cable, and make sure that nothing horrible was going to happen here. But this provided an opportunity. In some sense, the telescope still works while they're busy checking all the girders. The trouble is it can only point straight up. And this guy, Alexander Volkson, that's how it's pronounced, thought, well, this could be kind of useful. So if I don't care where I look, I can get an awful lot of time on the world's biggest radio telescope. I'll just look as the Earth rotates straight overhead. So there'll be a ring around the sky. We can look over and over again at this. And we can use this to look for pulsars. So that's what he did. Had a huge amount of time he would never otherwise have got had there not been this maintenance, and found a fair number of pulsars, including a millisecond pulsar.
So these millisecond pulsars are kind of interesting because they flash instead of, every 10th of a second or something, they're flashing at literally hundreds of times per second. And that's a funny thing to figure out how you can get one in nature.
So here's a simulation put together by the Australian Telescope National Facility. That is, you start with a binary star.
So you have a supernova, which creates a pulsar.
And the second star in the binary later turns into a red giant, and it feeds gas into the first one. As the gas spirals in, it gives it angular momentum, makes it spin faster and faster. You can see it going round and round faster.
So it's the classic conservation of angular momentum.
And eventually the second star will come to the end of its life. As in this simulation, it might end up as a pulsar itself, but a slow-moving one. But it might also just end its life as a white dwarf. So this is the normal idea about how you form these millisecond pulsars. You get a normal pulsar in a binary system, and it forms a normal slow-moving spinning pulsar after its explosion. And then the second star swells up at some later stage. It must be the less massive star, otherwise it would have exploded first.
Yep.
And dumps gas onto the surface, spins it all up.
And so what you're left with here really depends on how much stuff there's left in the star. If it was a little star that spun this up, then obviously it's not going to supernova. You have to be greater than 8 solar masses to explode as a supernova. But, depending on how much stuff gets dumped up, you could end up with anything here from a white dwarf to a pulsar.
So, the normal theory is that whenever you see a millisecond pulsar, it should be a binary with something near it, something that spun it up to these enormous speeds. I mean, just imagine something spinning thousands of times a second. It needs a lot of spinning to make it happen. Yeah. The trouble is, when people study millisecond pulsars, it turns out that some of them do indeed, like this one, have a second pulsar or a white dwarf near it, but a lot of them don't. They seem to be by themselves. And this is a puzzle that was well known in the early 90s. It's a real puzzle. How do you get these things spun up to these enormous speeds without something nearby to feed them?
Because we're almost positive there's no way in a supernova explosion to get them going that fast on their own. And even if you did, they would slow down, it turns out, due to their magnetic field slowing things down.
So Alexander decided to try and see if there was another binary companion, a white dwarf or another neutron star near this one. Now, how do you do that? Well, here is a pulse from this pulsar. It was pulsing every 6.2 milliseconds, and they can measure the time of the pulse to an accuracy of about 12 microseconds.
So this pulse is how many radio waves, how much energy and radio energy you're getting arriving here at Earth as a function of time.
So not much, not much. Whoa! Radio down a bit, up even more, then drop down, nothing, nothing, nothing. But the thing to bear in mind is you can measure when this pulse is coming with an accuracy of microseconds. And that's just one pulse. You have a pulse every 6 milliseconds. You get thousands, millions of pulses. What this means is you can measure with exquisite precision the timing of these things. And that gives you a clue to what's going on. Let's say it isn't a binary system. So there you've got the pulsar with, let's say, a white dwarf around it. Because of the reflex motion we've already talked about, the neutron star, which may be more massive than the white dwarf, is still going to be moving backwards and forwards. And when it's further from us, these pulses have a longer distance to go to reach us than when they're nearer, which means they'll arrive a bit later. So instead of all arriving at regular, when it's further away, they'll arrive late. When it's nearer, they'll arrive early. And given we can measure when these pulses are arriving to a microsecond accuracy, light only travels 300 meters in a microsecond. So that means we can tell the changes of distance to accuracies of hundreds of meters or even less.
And if you can take, because you can take so many of these measurements, you can actually average. And so a single pulse might do 300 meters. but I'm going to have 1,000,000 pulses, because this is doing, in 1,000 seconds, you get 1,000,000 pulses. That means that I can average down and probably measure things to better than a meter.
Yes, in fact, some of these things they can measure at relative distance changes to actually centimetre accuracies, better than you can do surveying on Earth. And this is a neutron star, at the other end of our galaxy. So, here's how Alexander thought we're going to find out if this thing has, as predicted, something like a white dwarf or another neutron star in it. We'll look for it to move towards us and away from us.
So we expect a giant sine wave, being many hundreds of meters per second would be my sense of the scale. Because
whatever it is that's near it, it's going to be very close because it's transferred matter over to it. So we're looking at something very close. It'll be orbiting quite fast, maybe on time scales of days.
Yep.
So expecting oscillation in days, and very large because it's a massive thing that's going to cause it to move quite a lot. That's what was predicted. Here's what was actually seen.
Geez, Paul, that doesn't look like a sine wave. It looks like a bit of a dog's breakfast, as we'd say.
Yes. So the first problem is it's not a clear sine wave. It's all over the place.
Yeah.
Second problem is we're talking about 2,000 microseconds, about 2 milliseconds. So we're talking again, kilometers, maybe.
So it's a kilometers variation. So that's not very much over a year, because this is almost a couple years worth of data. So
and it's too slow. So we're talking about timescales of months, not timescales of days, and we're talking about movement of kilometers, not kilometers per second. So it is moving, but it's not moving in a sine wave, and it's moving too little and on too slow a time scale.
So what's the solution here?
Well, if you look hard at that, maybe you can see a bit of a pattern.
There is a bit of order in the chaos there.
So Alexander was playing around with a model fitting software and played with it, and it clearly doesn't fit a single sine wave, but it turns out if you added 2 sine waves together...
Oh, so they beat in and out.
Yes, sometimes they line up together and give you a big pulse, sometimes they're going against each other and give a small one. But it seems that this thing's doing sort of 2 oscillations, one slow oscillation back and forth, and a faster oscillation back and forth superimposed. I don't know if I can do that sort of dance, try and do 2 dances back and forth at the same time. I thought probably too embarrassing to try, but that's what we're talking about here. So what's going on here?
Okay, so if you have a little planet and a big planet going around different orbits, it's sort of like a spirograph that I used to play for. You'll get interesting little patterns like that.
And it needs to be a planet, not a binary star, because if it was another star, the oscillations would be much bigger than this. So you need something that's further out, which means the oscillations happen on timescales of months rather than days, and it needs to be much smaller than a star. So like a planet, or 2 planets.
So not only do we have 1 planet where we shouldn't have one, we have 2 planets.
Okay, so let's go and see if we can actually work out what the properties of these planets are.